So that's a three-liner type of problem. Gauss's law, boom, boom, you're done. Okay, so I've done all cases of where you can apply Gauss's law, but I want to do this other more complicated problem, more complicated than what you're going to get over there. So what if you have a dielectric sphere with charge per unit volume rho that's proportional to the distance away from the sphere. So the radius of this is A, so it's a dielectric. All over the place. But suppose the charge per unit volume is not uniform, but depends on distance away from the center of the sphere. How about I make it alpha r cubed, just to give it some interesting dependence. So calculate E everywhere. Well, everywhere means at some point inside the sphere and at some point outside the sphere, right? Inside and outside. So let's do the inside first. Inside, that would be R less than A, right? So I write down Gauss's law. That's Gauss's law. And I want to know what is the electric field at some point in here that's at a distance r from the center. We are given a sphere. So what is the Gaussian surface that we should imagine passing through that point?
Sphere.
A sphere, right? So we imagine a sphere. So this thing in blue here is the Gaussian surface. All right. So, with the correct Gaussian surface, this integral on the left-hand side simply becomes what? What should I write down? What should I write down on the left-hand side of Gauss's law?
E
times 4 pi r squared. Correct. The area of the Gaussian surface, right? Now, on the right-hand side, I want the total charge enclosed the Gaussian surface. And the total charge is going to be the one in here. So what is the charge enclosed? Should I say rho times, which is the charge per unit volume, multiplied by that volume? Or what should I say? What should I do?
Should do alpha r cubed times the volume? Should you do alpha r cubed times the volume? No?
No, because this charge per unit volume depends on R. The charge per unit volume at the center is going to be 0. And then it's going to be something bigger. So as you go outside, well, not outside, as you go away from the center, the amount of charge per unit volume is different. So it's changing with distance. So the only time that I can just multiply the charge per unit volume times this volume is if that rho is the same there, same everywhere. But it isn't. So how do I find the charge inside the Gaussian surface? How do I evaluate this Q enclosed over here? So what is this equal to? Huh? I have to integrate. So what I need to do is, I need to choose, so I have to say this, that, let's see, maybe I'll use green. I'll use a separate, I'll do a separate calculation over here. So, this is the object or radius A, right? You get charge all over the place, right? I want the total charge enclosed the Gaussian surface, which is, let's say, this surface, or radius R. I want the charge inside of that. But the way that I find that charge inside the Gaussian surface is I have to select, I have to imagine a volume that's the surface of a sphere. I'm going to call it a different R, like this, and thickness, infinitesimal thickness, dr. So this thickness is dr. Notice this R is different from that R. This R in blue, that's the radius of the Gaussian surface. What I have here is an infinitesimal volume. So this is an infinitesimal volume, right? And the volume of that, I'm going to call it dV, how about I call it OL for volume. So my question to you is, what is this volume in green? I have a sphere of radius R and thickness dr. So what is that volume equal to?
It's infinitesimally small of the.
So what is the volume? I mean, the radius of the outer, the radius of this sphere is this R. And the radius of this sphere, the one on the outside, that one is R plus dr. So what's the volume between those two spheres? What do you think is that volume equal to? For what? For thirds? When we did the disk problem, when we were calculating, you have a disk and we were calculating the electric field on the axis, right? We took a ring, and we took a ring, a radius R, and thickness the R. In that case, we were interested in the area. What did we say is this area? What did we say was this area between this ring, 2 dimensions, or radius R, and thickness dr. Do you remember how we found that area? What was it?
2 pi r dr.
Exactly. It's this length so that the A was 2 pi r, and then multiplied by the thickness, dr. Now what we have over here is, well, this is not a ring, this is a sphere. So what will be the volume of that? That volume would be the volume, it would be the area of the inner surface, which is what?
4 pi r squared.
And then you multiply by the thickness. dr is the area of the inner sphere multiplied by the infinitesimal thickness. No? And then the charge in there, the charge in here, the dq in there, the charge in there is the charge per unit volume, rho, times that volume. So that would be rho, which is, in this case, alpha r cubed. Actually, it's r cubed, because I'm going to use that now. And then multiply, right, is the charge at that radius, which is radius r, multiplied by that volume, which is this volume. So this would be 4 pi alpha r to the 5th times the r. That's the charge in there. So that will be how much charge is in a volume of radius r and thickness dr. That's the charge in there. What I want is all the charge in this sphere of radius of this r. So it will be the charge in that volume plus the charge in the volume next to it plus the charge in the volume next to it plus the charge in the volume next to it plus the charge all the way up to radius A. So the charge enclosed is actually the sum of the charges in those infinitesimal volumes, spherical volumes. So this would be the charge per unit volume times the unit of volume integrated from r equals 0 to r equals r. It has to make sense. Don't memorize it. You have to think about it, picture it, and it has to make sense. If it doesn't make sense, don't stop thinking about it until it makes sense. Don't watch TV unless you understand that. It has to make sense in a way that you don't have to rely on memorizing it. You know, it's like, oh, this is what I'm doing, right? And then, so that you can then tomorrow, next week, next month, you can write it down correctly. Right? So, you cannot just multiply rho, which is the charge per unit volume. If it's uniform, then you can it's just the same amount in every unit of volume. It's the same amount of charge. So you just multiply rho by the whole volume. But in this problem, we do not have a uniform charge per unit volume. The distribution of charge is not uniform. It is dependent on R. So then what we need to do is imagine a sphere of this radius and infinitesimal thickness dr. And then the way that we are going to find out the total charge inside this blue sphere, which is the Gaussian surface, right, is by summing the charge that's green over there plus the charge next to it in green, plus the charge next to it in green, plus the one next to it, and you do that, all the way up to there, because that's what we want in Gauss's law, right? This is the charge up inside the Gaussian surface, and my Gaussian surface has this other radius. So I have to do this calculation, and that's what goes in the numerator. And then I solve for E. Then it's just algebra. So this calculation for the enclosed charge is the sum of all the dq's, right? Essentially it's that, which is the charge per unit volume times that infinitesimal volume, right? And this is equal to, the charge per unit volume is rho r cubed times the unit of volume, which is the volume of a sphere multiplied, the area of a sphere multiplied by the thickness. And then I have to evaluate from the smallest, sphere of radius 0 up to the radius of the Gaussian surface, because I only want the charge up to here. And that r is different. So then this becomes, the 4 the pi and the alpha are constants, but then I have r to the 5th dr from 0 to that r. So this is 4 pi alpha. What is the integral of r to the 5th dr?
The integral is 1/6
Not the
r to
derivative.
the
Not the
integral is
derivative.
1/6 r to the 6th.
It would be r to the 6 over 6. And then I have to evaluate this from r equals 0 to r equals that of the R. So this would be 4 6, which is what, 2/3? I'll write the 4 6 so you see where that comes from, pi alpha, and then this would be R to the 6. So this is 2/3 pi alpha R to the 6. That's the Q enclosed that needs to go in here. So then we have E times 4 pi R squared equals, and then we have 2/3 over here, pi alpha R to the 6. And then the next line is the answer. I cancel the pi's. I'm going to get 2 divided by 4 is a half. A half of a third is 1/6. So the answer is going to be 1/6, or alpha. Oh, and by the way, R squared and R to the 6 is going to give me R to the 4th and then a 6 epsilon naught. Yes? This is why they hire engineers in companies. It's too easy to just take rho and multiply by some value that anyone can look up. The question is, well, if the charge is not uniformly distributed, how do you figure out the total charge inside? And they hire someone who can do that calculus. So, now, what if we want to know the electric field outside? Electric field outside. What would we change? So, then, outside, so this would be B. This means outside the dielectric sphere where R is greater than the radius, right? So then we have Gauss's law is like this. And this becomes, so now your Gaussian surface, in fact, I'm going to draw it over here. We have, this is the radius A, and I want to know, this is what the charge is, right? And I want to know the electric field outside at some distance R away from the center. So over here, so this is my Gaussian surface. So this becomes E times the area of the Gaussian surface, which is 4 pi R squared. Now, what is the total charge inside the Gaussian surface? The total charge inside the Gaussian surface is the charge in the sphere, which is dielectric sphere, which is all of this, right? That's the charge. But what would that charge enclosed be equal to? Well, I can just use this result, right?
A change.
But what would I change? In other words, I would do this sum, but when do I stop the sum?
At A.
At the radius of the dielectric sphere, which is A. So the result is going to be? Because the charge is only distributed up to radius A, and so now that becomes 2/3 pi alpha A to the 6. So the pi cancels. So you get that the electric field equals. So 2 divided by 4 is a half of a third is 1/6. So that would be alpha A to the 6 divided by 6, and then you have an epsilon naught and you have an r squared. That's outside. Yes? Question? Yes?
So, you mentioned something about like engineers doing this in real life, but I was wondering, we have like, relative to real life, a fairly simple equation, like alpha r cubed. How would you even, in real life, derive an equation like that for the distribution of a charge, or is that like too complicated to ask?
Suppose they tell you this is the distribution, so
Oh,
figure
okay.
out what it should be. And I'm sure there's a program where you put it in and all of this is done. I mean, I could also do this, right? I could say, okay, well, it's been programmed that Q enclosed is the integral of rho times d volume, right? And that will be rho times 4 pi, r squared dr from r equals, in this case, 0, from some lower limit to some higher limit, let's say this r. Well, what happens is that if rho is constant and you plug it in, right, then rho just comes outside, and the 4 pi as well, and then you have the integral of r squared dr from 0 to this r. And that's just going to be 4 pi rho. And what is this integral equal to?
1 r cubed over 3.
Which is the charge per unit volume times that volume. So, yeah, if they give you something that begins with this, and then you just plug in the expression, then it'll give you the result that you would expect. I mean, this sort of calculation but before I make that comment, any questions?
Might be a little bit dumb, but where do we get the 6 in the denominator from? Is that multiplying the 2/3 and 4 somehow?
No. So it's 2/3, and then the 4 is here. When you bring it downstairs, it becomes like that.
Oh.
So this is 1/2. Yeah. Other questions?
What did you mean earlier when we were talking about the this is backtracking, the infinitesimal volume? Did you mean like the volume between the two spheres? Is that what we were talking about?
Mm-hmm.
And then it was like infinitesimally
And
small.
what makes it infinitesimal is that the thickness is infinitesimal, dr.
Okay. Thank you.
Other questions? I mean,
And then
this sort of, can I erase this now?
we did, just to be sure, we did the integral to find the like repeated infinitesimally small volumes.
So this is why this course is so good for you to take, because you get a different understanding of what an integral is. Well, different, but it's really the same. An integral is a sum. What am I doing with this over here? Why do I do this? It's like I have this ring over here. Well, I have this, right? And this is radius A, but then I'm considering this ring, well, not ring, it's actually in 3 dimensions, so it's a sphere of radius r and thickness dr. And then dq is the charge in there. But charge is a scalar quantity. The total charge is just this plus that plus that plus that plus that plus that. You don't have to worry about components, canceling, and so on. It's just this plus this plus this plus this plus this. that plus 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 is what an integral does for you. It's a summation. So I need to add that dq, I can call it dq1, and then to the next dq, and that's dq2, and then to the next dq in the next, infinitesimal volume, dq3, and the sum of all of this is the total charge. And that's what this is. It's the sum of all the dq's. So if you have a suppose you're told you have a line charge over here, right? This is from 0, x equals 0, to x equals L. And this is like an x-axis, right? And there is charge all over the place. From 0 to L. If the charge per unit length is lambda and is uniform, what's the total charge? What is all of this charge equal to?
Lambda L
Lambda times L. How did you get that?
by multiplying the charge per unit length times the length.
Okay, good. But does that make sense? Or is it just something you memorized? So essentially, it's, you say, okay, the total charge, I'm going to think of it like this. The total charge, right, is, I'm going to choose a dq in there over an infinitesimal length dx. Yes? So the total charge is going to be equal to this little bit of charge, dq, plus the next little bit of charge, dq, plus the next dq, plus the next dq, plus the next dq, plus the next dq. And I have to do that sum from here to there. So it's the sum of all of these dq's. That's the total charge. Now, if the charge per unit length is lambda, what is the charge dq in this little bit of length dx?
D lambda.
What is this dq? Let's erase this, so this is not in our. How much is the charge dq in this length dx? What's that? Lambda dx. It is the charge per unit length times that length. And when you write this expression, the reason why this is infinitesimal is you're saying this is so thin, so small, that this lambda over that length is constant, is uniform. But only over that length, right? So now, the total charge is going to be, well, the sum of all these dq's. So it would be lambda dx. Now, if lambda is uniform, a constant, everywhere the same, then you can put it outside the integral, and it's lambda dx. And this is an integral of x, so I integrate from x equals something to x equals something else. From 0 to L. And this is just lambda L. But what if I said that the charge distributed over here is not uniform? It depends with how far you are from x. So what if I say that the charge in there, lambda, is, well, it depends on x. How about I make it something like, suppose this is not uniform, but the charge per unit length is something like alpha x squared. So as I go further and further away from the center, the charge per unit length is bigger, 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 bigger. I cannot just multiply lambda times L because the charge distribution is not the same. So therefore, in that case, I cannot do this because this is not uniform. So then I have to say, okay, so lambda is given as some constant times x squared dx. Now, this is a constant that I can pull outside. So now this is going to be what? Alpha L cubed over 3. That's the total charge. This is along a line. What do you do if the charge is distributed over a surface, over an area? So what if on this wall over here you have a height of h, capital H, and a length of capital L, and the charge per unit area is sigma? What is the total charge on the wall? So now we go to another dimension. So now you have this thing, a wall, that's LH, right? And there's a charge per unit area sigma. You know, on this wall, there's charge all over the place, right? So what is the total charge? Now you might say right away what? Sigma times the area, which is sigma LH. Only if you have the same distribution of charge per unit area everywhere on the wall. Only then. Otherwise, how do you do it? Right? So then you have to say, like over here, okay, I am going to envision a charge per unit area here. So I'm going to take a unit of area. That's my dA. And I'm going to call this, given this geometry, a rectangular coordinate system is the easiest one. Right? Why use spherical coordinates or cylindrical coordinates? This is just rectangular coordinates. So I would call this dx, and I would call this dy. And the charge, you know, per unit area is sigma. What if sigma is uniform? Suppose it's uniform. What would be the amount of charge in that blue little square? What's the charge in here?
And it would be sigma dx dy.
Sigma times dA, right? Right? So therefore we could say that Q equals, it's the charge dQ over that little square plus the next one, plus the next charge, plus the next charge, plus the next charge, plus the until I fill up the entire wall, right? So it's the sum of all those dQs. And then rho, this dQ is the charge per unit area times that area. Now, what's a good expression for this area? What's the area of that?
Dx dy.
Exactly. Now, if sigma is uniform, then it doesn't matter where on the wall I am. It's the same everywhere. So therefore, I can take it outside. And this becomes sigma times dx dy. And, well, here they're separated. I can do a double integral from y equals to y equals, from x equals to x equals, right? So suppose I choose the x-axis to be here, the y-axis to be there, right? And this is the origin. So I integrate x from what to what? To cover the whole wall.
0 to L.
0 to L. And y, I integrate from where to where? 0 to h. Right? And so this becomes sigma. Now, what is the integral of dx from 0 to L?
L.
And what is the integral of dy from 0 to h?
H.
Right? That's the total charge. Which you might say, you know, from the very beginning, oh, just sigma times A. But what if sigma is not uniform? What if sigma is not uniform, but rather it has a dependence on the x-axis and a dependence on the y-axis? Suppose sigma is given as alpha times x squared times beta, another constant times y cubed. Maybe how the charge is distributed horizontally, right, is not uniform, but it increases with the square of the distance. But vertically, it's not even the same. It doesn't increase as the square of the distance, but as the cube of the distance, where alpha and beta are constants. So what will be the total charge in this thing? Well, you just don't take it outside over here. Instead, well, you say, no, I cannot take that outside, so I have to keep that in there. And you say, well, sigma is given by this, alpha, beta, x squared, y cubed, and then you have dx, dy, right? So this equals, the alpha and the beta are constant, so those you can take outside, and then you can separate x squared dx and y cubed dy. And then you put in your limits like before. So x is from 0 to L, and y is from 0 to h. And this becomes, and this is going to be what? L cubed over 3, right? And what about this one?
H to the 4th over 4.
Exactly. So this would be alpha beta over 12 L cubed h to the 4th. That would be the total charge in there. Now, we did the disk, right? We did the disk. The disk was not rectangular like this. The disk was like that, radius A, right? And you had charge all over the place, right? So we had a sigma in here. Well, what is the total charge in here? What's the total charge?
dq sigma.
And this is uniform. Let's do that first. What should be the answer?
Sigma 4 pi r squared.
It's a disk,
Disk.
not a sphere. 2 dimensions.
Just pi r squared.
By who?
E squared.
A squared. Yeah, the radius, which is A. Right? But what if sigma is not constant, distributed, plastered on this disk in a way that's constant, but maybe it's got a dependence on R. So how do you do it in that case? So then you have this. The radius is A, and you have a sigma in here. Suppose sigma is alpha R to the 4th. Or did we do to the 4th? How about we make it to the 7th? Maybe you like Cristiano Ronaldo. You like a 7 in here. So there's a charge all over the place. Right? So it's not uniformly distributed. There's a dependence on distance. So again, what is the Q? The total charge Q is going to be the sum of all the dQs. Now, it is not convenient to choose an area dx dy, because you're going to run into trouble at the edges. A better infinitesimal area to choose is to say no, and to use polar coordinates in 2 dimensions, right? So you say, okay, I'm going to choose this. The radius of this is r, and the thickness is dr. So what is this charge in here? So what's the Q? Equal to. So over this infinitesimal thickness, since the charge period area depends only on distance, over this infinitesimal thickness is like R is constant. So you just say it's just that sigma times that area of the area of this thing in this area in blue. Now we worked this out, I think it was last week or the week before that. What is that area? What's the area of this ring of radius r and thickness dr? It's like the length times the width. 2 pi r is the circumference times the width dr. So this would be sigma times 2 pi r dr. That's the amount of charge in this ring of infinitesimal width dr and radius r. But what I want is the charge in all of this disk. And since the charge is not distributed uniformly, I gotta find out the charge in that ring, plus the charge in the next ring, plus the charge in the next, and the next, and the next, and the next, and fill it up. And the contributions are not the same. So I cannot take sigma outside the integral like I did over there. So now you just keep it inside, right? So then you say, okay, this is sigma dA, and dA is this. And now I'm going to integrate from, you tell me the smaller radius and the other radius. This could be a washer with a hole inside from radius A to radius B. Or it could be like a disk from 0 to A. And then you put out the constants, the 2, the pi, the sigma. Sorry. I forgot that I was thinking of Ronaldo there. So you have what? Alpha r to the 7th. That r is that r, right? Oh, maybe I'll just do this so that you're not confused. Times 2 pi r dr from 0 to A. So Q will be the 2, the pi, and the alpha I can take outside, and then I have r to the 8th dr from 0 to A. This would be 2 pi alpha, and this would be 8 to the 9th over 9, right? But you get the what we're doing? So if you have disks, polar coordinates are more convenient and easier, I think, than rectangular coordinate system like dx and dy. But if you have like a slab like this, that's rectangular. Rectangular coordinates are more convenient. It's easy. It's more easy to see the limits of integration. So the problem that we had was not a line, it was not a wall, it was a sphere. So now the charge per unit volume is rho. Right? So that's the problem that we were doing. On the right-hand side of Gauss's law, you have the charge enclosed by the Gaussian surface. So your limits are determined by where the Gaussian surface is. So you just want the charge inside of that, right? So we had what? A sphere, a radius A, right? Suppose you have a sphere radius A, right? So the radius is A, and you have charge all over the place. Now you're given a rho, charge per volume. So suppose this is uniform. Suppose this is uniform. So what's the total charge in here? Now you may figure this out quickly like this because rho is uniform. You can take the shortcut. It's just what?
Rho 4 pi r squared.
It's just that. Now, suppose rho is not uniform. Like, I don't know what I said. I think I said, suppose I said alpha r cubed or little r cubed. So then what is q? Then this is not correct. So then you have to select an infinitesimal volume, because now you're in 3 dimensions. You don't choose an infinitesimal area. You don't, like in 2 dimensions, you don't choose an infinitesimal length like we did in the case of the wire. So now your infinitesimal volume is going to be, let's say, radius r and thickness dr. So now I'm interested in the volume over here, dV. I could just call it dV, but there's a reason why I'm taking the trouble of writing volume, because you'll see why in a little bit. So now, what is that volume contained between the sphere of radius r and the other sphere outside with radius r plus dr? So the thickness is what's infinitesimal. So volume is what? Area of the base times the height. Think of this as the base, and the height is dr. So what is the area of the base? We're talking about a sphere.
4 pi r squared.
4 pi r squared. And what is the height?
dr.
Then you multiply by that. And now the total charge is, it's the charge in that infinitesimal volume, well, added to the charge in the next infinitesimal volume, added to the charge in the next one, added to the charge in the next one, and blah, 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 all of them. And that's what the integral is doing for you. It's doing that sum for you. Right? And so this would be what? It would be,
Integral.
so the charge in here, dq, would be what? See, because this thickness is infinitesimal, you assume that rho is constant over that infinitesimal thickness. So it's just the charge per unit volume times that volume. So this would be rho times the volume. And now for rho, now you use the expression that was given. I mean, suppose, well, if it were constant, what would you get? Put it outside, it would be rho times the sum of the volumes, which is 4/3 pi r cubed, 4/3 pi a cubed, right? But now you do alpha r cubed times, now the volume is what? Infinitesimal volume is 4 pi r squared dr. So this equals, I can put out the 4, the pi, the alpha, and then I have r to the 5th, like that. And I integrate from r equals what to r equals what?
From 0 to a.
In this case, from 0 to a. When we were doing that other problem, we integrate from 0 to r because we were inside the, the sphere and wanted the charge inside the Gaussian surface. So the Gaussian surface there puts the limit. Here I'm just calculating the total charge. So this would be 4 pi alpha. And what is that integral going to be? So this would be 2/3. Yes? And this is something you're going to see again and again and again and again and again in your engineering courses. You're going to have to select infinitesimal volumes, infinitesimal areas in the various coordinate systems. Right? So, we can argue as to what would happen if the charge per volume not only just had a dependence on radius, but also on angle. There's an azimuthal angle and there is a polar angle. And then you use spherical coordinates. And then this integral, instead of just becoming an integral over one variable, it becomes an integral over 3 variables. So you do triple integrals. And when you take calculus 3, you're going to learn about triple integrals and so on. And the various area elements, volume elements in the various coordinate systems. So all of that is very, very important.
Professor,
Yes?
would you consider moving the quiz to Monday?
But it's not going to have this. It's just Gauss's law.
I know.
It's the line. Oh, oh, and that's it.
Okay.
All you need to know is, so what, the only things that I can give you are what? Spheres and cylinders. Because if I give you the
The plane?
infinitely large sheets, then, the only thing that I can give you is to derive the result, or give you 3 sheets and then you have to remember the result and apply it. But, maybe just, I'll give you a problem which is either going to be a sphere or a cylinder, and rho is constant. That shouldn't, that'll force you to not be behind. And I started with this today. Because Sharif, is it? Came to office hours today and asked me, there's a homework problem like this, but having to do with a cylinder. So I said, instead of doing the cylinder and doing the homework for them, I'll do the sphere. In the end, it's the same concept. And we need Gauss's law for what I'm going to be talking about, well, this week on chapter 23, because you need that for chapter 23. Okay? So it's a short quiz. You should be able to be done in 4 minutes, or maybe 3. By the way, I was generally disappointed with the first quiz. I think of, 47 of you or so? I think only about 5 people got a perfect score, which is very, very low. I think only about 5 people got a perfect score. 5, 4, 5, 6 at most, I would say. So, if you started out drawing the electric field vectors in the wrong way, for me, I don't need to look at anything else. I mean, it's like that bad already to start with. Okay, so, and then many of you actually calculated the individual electric fields, but you never calculated the magnitude or the direction. Some people wrote this, and they gave me a number, but then what's theta? From where is it measured? Is it measured from the positive x-axis, going clockwise, counterclockwise? I mean, there's a picture like this, so which is theta? Is theta this? Is it that? Is it this? Is it that? Is it this? Is it that? So you have to show me in a diagram, right? Go like this, that's the theta that I'm talking about. So you have to show me, you cannot just say theta is, some number. So from where? Are you measuring that from the positive y-axis? From the positive x-axis? From the negative x-axis? On which way you're going, clockwise, counterclockwise? So you must show me that in a picture. Right? So, and I don't care which angle you give me as long as you show it to me. Right? You could also say, for example, instead of this, right, you could do the calculation and then say, like that, and suppose this is missing there. And then this is, 57 degrees, whatever. And this is E net. And so, actually, you don't need this in there anymore, but you have to explicitly tell me, you have to answer the question, right? The question asks specifically for the magnitude and the direction of a vector quantity. So I wanted to see a diagram clearly specifying the direction, or you could say it in words, right? Some people actually did, right? Some people did that. Some people said, it's so many degrees from the negative x-axis and blah, 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 blah. That's fine, as long as you describe it and you explicitly write down what the answer is. But if I ask you for an electric field with magnitude and direction, and you give me just the electric field in component form, that's fine. I think you got 10, 11 points, but you didn't answer the question. I asked specifically for the magnitude and direction of the electric field. Okay, so. And I can only give partial credit for things that are right. But if the beginning is bad, then I don't really want to look at the rest because it's just bad. You just started off wrong, and so it's just bad. Okay. So, if you're having a little trouble with this, maybe it's the first time that you've actually seen it like this. So look at it, put what you just wrote down aside, and then do it. Don't look, and then compare. And because it's very, very, very important to know those, what's going on over there. Why do you set it up the way that you set it up? And then once you understand it, then it'll be a lot easier from then on. So there are some things like vectors in chapter 1 of the textbook. You should, when you learn about it in chapter 1, you should really learn them. Because otherwise you're going to stumble again and again and again and again and again and again, later on. Because you never really learned them the way you should have learned it. Or you thought you learned it, but not, you really didn't learn it so well. So. Okay, so we want to use energy arguments to analyze the motion of charged particles in space. So, physics 280 is challenging on many counts. For one thing, it's very abstract. Who's ever seen an electric field or even felt it? An electron running from here to there, right? So we're going to be talking about electric currents in wires, but you just probably touch it, then you get burned or electrocuted, but you don't really see the thing running, right? And it's not like a river where you see the water flowing, right, and so on. So it's very abstract. So you have to imagine a lot of things, and there are many more things to connect as well, because in physics 185, it's, the fundamental force that you talk about over there is gravity. But gravity is only conservative. I'm sorry, it's only attractive. It is also a conservative force, but that's not the comment that I wanted to make. But it's just an attractive force, right? Exerted by, it's also only attractive because it's due to objects having mass, but the mass of an object is only of one sign, right? Positive, and that's it. But with electrical forces, right, and electrical charged particles, well, there are two signs. They're positive and they're negative charges, right? So the forces could be attractive or repulsive, so there's more to it. And if the charges are moving, right, you can also talk about a magnetic field. So we will talk about magnetic forces in addition to electrical forces. So there's more to discuss, right? Magnetic forces, electric forces, right? And then you have positive and negative charges. So there's just more details. There are many more things to connect. In physics 185, as hard as that course is when you take it the first time, or when you take it, right, in the end is, the work energy theorem, the F equals ma, right? But here you have to connect many more things that are also abstract. And so it is very important that you don't fall behind. It is important that you read the book. But I don't know how many of you actually read the book, the textbook that is, right? These notes that I wrote over here at some point, when we didn't have projections like this onto a screen, I used to write this on the board. So what you see here is what I wrote on the board. And to save myself time writing on the board, instead I'd rather use the board to solve problems, right? So then I type this up also mainly to guide me, okay, this is what I should cover next, and so on. But I didn't write this thinking that this is going to replace the textbook. By no means, right? So read the textbook, and then think about what the main idea of the chapter is. Maybe there are 3, 4 concepts that you need to learn in that chapter, and your challenge is to figure out, well, what are those 3, 4, 5 concepts that I need to learn from this chapter? If a friend of mine couldn't go to school, couldn't go to class, and my friend asked me, teach me that chapter because we're going to have a test and I don't know anything about that chapter, what would you teach them? What would you tell them? This is what you need to know about that chapter, right? And without looking at anything, you need to know this without looking at your notes. When you can do that, then start doing the homework problems. Now, all of that is very time consuming, of course, and that's where the challenge comes in. So, finding time, so anyway, but if you're struggling, well, you may have to dedicate more time to it. It's not that you're not cut out to do this type of work. It's just that you just have to spend more time. You're probably not spending enough time. And I'm not saying, shame on you for not spending more time. I know that people have jobs, right? Or a family, right? There are many issues that, that you have to take care of. School, right? So there are many things that may keep you from spending more time on this work, but it's, if you can find the time, then by all means, focus on it. It's a challenge, but it's doable. You do it again and again and again, and you have to discover what is the method of studying that best works for you, because my method, it may not be the best one for you, right? So we all learn slightly differently, but either way, you have to spend time on it. If you think you're just gonna come in, write my notes, and study them before a quiz, you're not really getting the most out of it. Okay? So just keep that in mind. Any questions? So, I don't know if I ever shared this with you, but when I was an undergrad, when I took this course, it was this one, Physics 280, equivalent. Actually, it was Physics 280 together with 285. In 19 weeks, we did the 2 courses. From chapter 21 through chapter 40, same textbook. And the final was truly cumulative, right? But it was very hard. It was a lot of work. I was always behind, always. And I had the blessing that I didn't have to study. I graduated from high school, and I won some scholarships, and so with that I had money to spend to buy my token, subway token to go to school by train, buy some things for myself. But I lived with my parents, and I didn't have to pay rent, so I didn't have to pay them for food. So that made it very, very, very easy, right, for me. Well, compared to many of you who, you have to work and you gotta pay rent. So I don't know how I would have done it, but I really admire you, those of you who work and have all of these other things that you do. It's just, I really admire you for that. But looking back at my case, we lived in a 2-bedroom apartment in the Bronx, and I have 5 brothers, and a lot of people in a small bedroom. A small bedroom and a small apartment, and finding, my school at that time didn't have dorms, so I lived with my parents in the city, in the Bronx. I went to school in Manhattan, and so it was, there were many challenges, and I could never study at the library. I finished class and I had to go home. That's how I just I went home, and I gotta figure out how to study over there, but that's what I did. But it was, I remember I used to study every evening from like 7 p.m. until midnight. On Saturdays, I would study from like 8 in the morning until 9 p.m. That was my Saturday. Right? By then, your head is going nuts, and you go out to a party, come back at 3, 4 o'clock in the morning, wake up at 11 on Sunday. But I would study from like 12 noon until around 8 p.m. And then it would repeat. And sometimes I said, nah, I'm going to go out to a party on Fridays, for example. And then, oh boy, did I regret it. Only one party a week is enough. Then, I was on vacation, and then you go to a lot of parties and you do a lot of things that you don't do when you're studying. But, I didn't have to work. I had the help of my parents, and I had scholarship money. But it was also, very, there was a lot of stress involved, right? In the beginning, you're struggling with this course, and, am I cut out to be a physicist? Am I smart enough? You begin asking all of these questions, right? Should I change my major? But what would I do? This is what I like. And so, you have all of these questions. And anyway, just stick it out and give it your best. Whatever happens, at least that's what I did. That's how I used to think. I would say, well, if I fail, I fail. But at least I'll know that I gave it my best. And I'll be okay with that. Sometimes people drop out from school and others look at them pretty bad, like, oh, I don't see it that way. It's, this is something that you dedicate your time to for years, not, a week or 2 weeks, but it's years, right? So just don't give up. But you gotta do your work, you gotta do your part. And if you need help, go look for help. Today I sent out an email. They have the OCC Success Center, and Van Vu, he took Physics 185, 280, 285 from me. And this guy is just amazing. He's really, really, really very, very bright. I don't think he ever lost a point in anything in the 3 courses, in the quizzes, and the lab reports, and the exams, and ever. And if I put an extra credit, he got it by 2. Very, very bright and very courteous, very nice, very matured, explains things very well. So, use him. He's got some time over there where he's working as a tutor. And, actually that's something that I did in my 3rd year in college, 3rd and 4th year in college. Then they finally opened up a physics tutoring center at my school. They had a math tutoring center that I always went to when I was taking my calculus and math courses, but they didn't have one in physics, which is what I really needed help with, in my 185, 280, 285. So instead I used to go to the office hours of the 3 professors who were teaching the 3 sections of the course that I was taking. Shalovsky, Miller, Kaku. And I used to go to their office hours. One of them had an office hour like at 8 o'clock in the morning. It was terrible, but I made it, to his office hours. Because that was the only people that could help me. I didn't know of any tutors. No one in my family had taken physics before, so I couldn't get help from anyone. It was just the textbook, the notes from the professor and myself, and the other 2 professors who had office hours. So I went to all of their office hours, to get my answers to those questions that I had. So I didn't, have help. So, but then when I was in my 3rd year, one of my classical mechanics professor, he said, we're opening a tutoring center of physics, and I want you to be in it. And I said, oh, good. So, and then we'll pay you. Oh, good, that's even better. But I was thinking more of, if I tutor, if I have to teach it to someone, I'm going to learn it. Because I have to learn it to teach it. And so to me that was like, good, then I'm going to review Physics 185, 280, 285, and then by helping others, by tutoring them, then it was like staying in and staying in and staying in, and like that. So if you teach it to someone, if you form study groups and so on, and you teach it to someone else, you begin to think about it in a slightly different way. Right? Maybe you explained it and the person didn't get it, right? And so you said, now I'm going to try this other thing, right? And then you come up with another way of looking at the problem. So if you can tutor, then by all means, it's a very, very good idea, I think. That way, when you take your engineering courses and you transfer out, all of those integrals by parts and so on, if you tutor math, for example, since you tutor them, then you're going to have that, there. You don't have to go back and review so much. Because you will have been doing it again and again and again by teaching it to other people. Anyway, chapter 23, we'll deal with electric potential. Electric potential is not a vector quantity, right? So what we were saying last time in class was that a charge generates something around it, right? And you can describe that something in terms of an electric field only if that electric field is going to be used to then calculate the force that this charge exerts on another charged particle. So the electric fields are used to calculate, forces. F equals QE. Now, what happens if I want to analyze the problem, but I don't want to make use of the electric, I'm not interested in the forces acting on the particle, but I want to use energy arguments. Then, when the other charged particle is placed over here, then I want to know what the energy of it is. And before I calculate the energy, I want to know what this produces over there that will then be used to calculate the energy of another charged particle placed over there. And that's called electric potential. The symbol for it is the capital letter V. So electric potential it's actually called also a scalar potential because it is a scalar quantity. It is not a vector quantity. It's not a vector quantity, it's a scalar quantity. It's either negative, 0, or positive. But it doesn't have any direction associated with it. That's why over here you don't see an arrow pointing this way or that way because it's not a vector quantity. There's no direction associated with it. So if there is a point charge over there and you want to calculate the electric potential that it produces over there, the expression is KQ over R. No square in the denominator. The electric field was KQ over R squared. This one doesn't have the square and there's no direction. So if the charge is positive, you plug in a positive number over there for Q. If the charge is negative, you plug in the negative sign and you're going to get a negative potential. Okay? So let's use this. Consider this example. Consider a point charge Q equals plus 3 nanocoulombs fixed in space. All right, so let's say it's fixed right here. So that's Q, it's plus 3 nanocoulombs. And what I want to know is, what is the electric potential that it generates over here, which is 1 meter away? There's nothing there. Over here, which is 2 meters away, and 3 meters. So what is the electric potential right here? How about I call it V1, generated by this charge? Maybe let me give this charge some color. So what is the electric potential that it generates at a distance of 1 meter away from it? So electric potential is what? K Q over R. So that would be 9 times 10 to the 9 times the charge, which is 3 nano, means 10 to the minus 9 over R. And that is what? 27 over r, correct? So just give me the distance and I'm going to tell you what the electric potential is. So 1 meter away, the electric potential is going to be 27 divided by 1. So this will be 27 volts. What if I want to know the electric potential that this charge of 3 nanocoulombs produces at a point that's 2 meters away from it? What would that be?
27 over 2.
How much?
27 over 2.
Which is?
13.5.
Exactly. Is the potential getting bigger or smaller as we move away from the charge?
Smaller.
Smaller. And what about 3 meters away from the charge? What is the potential right there? In case I'm interested in the potential there. Volts, correct. So what? This charge produces an electric potential everywhere around it. Here, there, everywhere around it. There's an electric potential. I'm just interested in these 3 locations or these 3 points. Why? Because I want to then bring another charge into the discussion. I want to bring another charge, and I'm going to put it either here, or I'm going to put it here, or I'm going to put it here. Actually, I could put it anywhere, but you know. Let's see what happens when I place that charge at these other locations. So what will happen is this. When a charge is placed, when a charge Q is placed in a location where the potential is this, that potential will be generated by another charge. Because this potential could not be the potential generated by this charge. Why? Because what if I ask you, what is the potential generated by this charge right there where it's at? It will be 27 divided by 0, which is undefined. I can tell you what the potential is that it generates at locations around it, but not at it, because I will be divided by 0, and it will be undefined. So, when I place this charge over here, true, this charge itself generates an electric potential around it. Right? But when I place the charge in there, when there is already a potential there, generated by some other charge, this being external over here generated by some other charge that's not even in the picture, but it is generated by some other charge. So when I place this charge in this location where there is this potential already, then this charge has potential energy. So there's a difference between potential and potential energy. And what is the potential energy of that charge when I place it there? It's going to be the charge that I place there multiplied by the electric potential there. So let's say that I bring in another charge, right? I don't know, I take it out of my pocket. And now I'm going to put that other charge over here. And suppose that charge is, I'm going to call it Q prime, it's minus 2 coulombs. I'm going to choose a big charge now so that it's easy to do the math. So what would be the electrical potential energy of this charge Q prime when I put it right there? It would be what? So the potential energy would be, should we say the electric potential when it is at 1 meter away? So what would it be? It would be that charge multiplied by the potential there, which is minus 2 multiplied by 27. And this is going to be what? Minus 54 joules. So if I place that charge Q prime right there, 1 meter away from the other charge, the electrical potential energy, and this is really the energy of Q prime as it interacts with this other Q. It's really the energy of interaction between them. Now, suppose I decide, well, you know, I'm not gonna put this charge over here. Instead, I'm gonna put it right here. So if I put it there, what would its potential energy be? Let's say U2, because it's 2 meters away from the other charge. Let's just use that notation. What would it be? So, you know, U would be Q prime times B, right? External to it. So it would be the charge that I placed there multiplied by the potential there, which we already calculated. It's produced by the other one, and it's 13.5 volts. So what is the potential energy? -2 times 13.5. So this is going to be minus 27 joules, correct. And what if I came and I said, no, I'm not gonna put it there. I don't want it. I don't want to put it there. I feel like putting it here. So Q prime is minus 2 coulombs. Now, when I place the charge over there, what would its potential energy be as it interacts with the other one? It would be minus 2 times 9 volts okay? So, all I'm saying is this. This charge over here is fixed. I'm not letting it move. I'm not allowing it to move. This is fixed. And then I calculated at these 3 locations what the electric potential is that's generated by that charge. So we got 27 volts, 13.5 volts, 9 volts, right? Now, why did I bother to calculate the electric potential there? Because I could take another charge and place it at either one of those 3 locations. At any one of those 3 locations, right? If I put that charge over here, its energy would be, its potential energy, minus 54 joules. If I put it here, it would be minus 27 joules. If I put it there, it would be minus 18 joules. Of those 3 locations, at which location would it have more potential energy? 1 meter away, 2 meters away, 3 meters away.
Is it the farther away?
Hmm?
So 3 meters away?
This one. The charge is still the minus 2 coulombs, right? So where would I place it? Here, 1 meter away, 2 meters away, or 3 meters away, so that it has more potential energy, more electrical potential energy. You have the electrical potential energies on the board. I'm asking you which one of those values is the greatest value. What's the answer?
Greatest potential is at 1 meter for 27 volts, no?
Which number is bigger, minus 18 or minus 54?
Minus 18.
Yeah. The more you are to the right in the number line, if this is the number line, 0, 1, 2, 3, minus 1, minus 2, minus 3, the more you are to the right, the greater the number. So minus 18 is going to be like over here. Minus 27 is going to be like, you know, over there, and this would be minus 54. So this is the bigger energy value. So if I place the charge over here, it would have more potential energy than if I place it at 2 or 1 meter away. So suppose I take that charge of minus 2 coulombs, and I say, you know what, I'm gonna put it here. And I'm going to hold it there. And I'm going to let go. So that it starts from rest. You know, the initial speed is 0. I just, you know, that one is fixed, that one is always at rest. I hold this charge over here, it's like, I feel something, right? And then I let go, starting from rest. Which way do you think that point charge Q prime of -2 coulombs is going to move? Do you think it's just, actually it might even just stay there, or do you think it's going to move to the right, it's going to move to the left? What do you think? Why to the left? How do you know it's going to move to the left?
Opposite charges attract.
So the positive charge over there attracts the negative charge. Is that what you're saying? Okay. What's that? That's another argument. So there are 3 ways to come up with this answer. One is to say, well, that's a positive charge, this is a negative charge, this charge is attracted by that one, it's going to go to the left. Yes?
Yeah.
Good. Another way, which we discussed in chapter 21, is, well, if this thing is going to move somewhere, it's because it experiences a force, right? Now, I remember minus and plus attract is going to go that way. But I could also say this. Well, if I want the force on that charge, right? What does that charge over there produce over here that will exert a force on this? An electric field. And which way is electric field over here pointing? Generated by that one. It's a positive charge. So which way is electric field here pointing? Away from it, right? So there's an electric field over here generated by that one. Because that's positive, it's away from it. But the force on the charge Q prime is given by that. But because this is negative, right? Then these 2 vectors have opposite directions. Since the electric field is to the right, because that charge is positive, and it generates an electric field pointing away from it, then the force on it is going to be this way. And therefore it's going to go to the left. Same conclusion. Yes? And the third argument is what she said. This thing started from rest, right? It's like as soon as I let go, this charge says, oh, I'm free, kind of. At least it's not holding me anymore. It says, so what should I do? I can just stay there, hang out over there, or I can go that way, or I can go this way. And but what happens if I go that way? If I go that way, my potential energy is getting bigger or smaller? Bigger. And in nature, if something is at rest and it's got some potential energy and you leave it alone, it's never going to go to higher potential energy. It's like, if you consider this marker, right? And I hold it this high above the floor. This marker is like that charge of Q prime. And I'm going to let go. Well, why does it go down? Why doesn't it go up? What did we say relative to this floor is the gravitational potential energy of the marker? mgh. Right? So the marker says, okay, he just let me go. So what do I do next? Do I stay here? Do I move up away from the earth? Or do I move towards the earth? It says, well, if I move up, I'm going to increase the height above the earth. So my gravitational potential energy is going to get bigger. No, it never does that. It always seeks location where the gravitational potential energy, where the potential energy is going to be less. So it's like the marker, as soon as I let go, it says, if I go up, mgh, the height is going to increase. I'm going to have more potential energy. I don't go there. If I stay here, that's fine. At least my potential energy is not getting bigger. But, gee, I have the freedom to go down, and my potential energy is going to get less because the height is less. And so it goes down, 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 down. And so the more it goes, the more it realizes it can still go down, and it goes down, 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 down. Now, what's happening as the marker is falling? The gravitational potential energy is getting smaller, 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 smaller. Overall, energy is conserved. So what's becoming of that gravitational potential energy that is decreasing? Is getting converted to another form of energy. Which energy?
Kinetic energy.
Kinetic energy. So the more it falls, the faster it's going to be moving, because the more it falls, the more height it lost, the more gravitational potential energy is getting converted to kinetic energy. So as the kinetic energy increases, 1/2 mv squared, it speeds up, speeds up, speeds up, speeds up, speeds up. So it's going to be the same thing with that mark, with that charge over there. When I let go of it here, there's no kinetic energy. The only way that I can have this marker go up is if I throw it upwards. I give it some kinetic energy upwards. I mean, if I throw it upwards, right? Otherwise, I can do this for the rest of my life. And this thing is never going to go up by itself. I can do this forever. It's not going to do that. Unless I have to throw it. So this marker over here, I released it from rest. Now it's like it's going to sample the space around it, and it's going to say, well, I don't have any kinetic energy to start with, so I'm going to go with, I'm going to lower my potential energy. So it's like it says, if I go that way, my potential energy is going to increase from minus 27 joules to minus 18 joules, which is a bigger potential energy. That would be like the marker going upwards in the case of gravity. But it says if I go that way, when I get over here, my potential energy is going to be minus 54 joules. That's lower. Ooh, so I don't want to go that way. And so it's going to go this way. And so this charged particle is going to go this way. But what happens as it goes closer to the other charge, it's losing potential energy. The potential energy is getting smaller. But what is becoming of that potential energy? Kinetic energy. So it's going to be speeding up, speeding up, speeding up, speeding up, speeding up. And then we can actually calculate how fast it's going to be traveling at the instant that it passes that point. Maybe I'll call this V2, 2 meters away, and this is 1, 1 meter away. We can calculate how fast it's going to be traveling when it passes that point. Suppose the mass of the marker, not the marker, the charge is, should we make it simple, 1 kilogram? That's a big charge, right? But, just we don't need calculators. How fast is that charged particle Q prime going to be moving at the instant it passes over here? We could do this in our heads. How much energy, how much electrical potential energy is going to be lost as it goes from 2 meters away from that charge to 1 meter away? How much potential energy is lost?
27 joules.
27 joules, right? And what's becoming of those 27 joules?
It's being converted into kinetic
Kinetic energy. So 1/2 mv squared has to be 27 joules. The m, I made it 1. So V is going to be the square root of 54 meters per second. Or, if you want to do it more formally, you say this. I remember my physics 185. I loved it so much that I remember the work energy theorem. Right? The initial energy plus the sum of the work done by the non-conservative forces is equal to the final energy. Now, there's only one force acting on this particle, and that's the electrical force. Well, it's a conservative force. Magnetic forces, electrical forces, gravity, and the elastic force exerted by a spring, they're all conservative. So nothing else is acting, so there are no non-conservative forces acting, so E initial equals E final. Well, what is the initial energy? It's the initial kinetic energy plus the initial electrical potential energy. What is the final energy? It's the final kinetic energy plus the final potential energy. Okay, so this is the initial here, and this is the final. So what is the initial kinetic energy? It's not moving initially, right? And what was the initial potential energy? Minus 27 joules. What's the kinetic energy when it gets to the final position? 1/2 times that speed squared. We could call it final, I guess. Plus, what is the electrical potential energy when it gets here? Minus 54. And I can bring this over here because I'm solving for that speed. So I get 54 minus 27 equals 1/2 m prime, which is 1, v final squared, and you get the same result. V final is the square root of 54. Yes? Yes? No? By the way, I've put problems like this in exams, and people lose all the points because they make the following mistake. And I want you to be aware of it so you don't make that mistake. I don't like it when students make mistakes. I mean, not that I don't like it, it's just that, you know, I get sad, right? When they lose all the points, right? So what they do is this. They say, oh, I want to know the speed over there, right? Let's call this V final instead over here, right? So then they say this, oh. So what I'm going to do is wrong. It's the wrong way of solving the problem. So you learn from other people's mistakes. So they say, oh, I'm going to use V final squared equals V initial squared plus 2a delta x, right? And so it starts from rest plus 2. Now what's the acceleration? Well, gee, what's the acceleration? And then delta x, they say, went from 2 meters to 1 meter, so that was 1 meter. Now, how do they find the acceleration? Well, they'll probably do something like this. Is the force, electrical force, divided by the mass. Now, what's the problem here? What is the electrical force that this charged particle exerts on this charged particle? That's a chapter 21 question, right? That's what? K, Q1, Q2 over R squared, right? So this would be 9 times 10 to the 9th. Q1 is 3 times 10 to the minus 9. Well, what about the Q2? Well, you might want to put minus 2 over here, which, do you know what that means? And then you have the mass, which is 1 kilogram, but then you have R squared. Now, what's up with R? When the particle is here, R is 2 meters. When the particle is here, R is 1.5 meters. When the particle is here, R is 1 meter. So R is changing as the particle moves, as the charge Q prime moves towards the other charge. So because this is changing, this acceleration is not constant. Because as it gets closer, 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 the force is bigger, 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 bigger. So the force is not constant. So the acceleration is not constant, and if the acceleration is not constant, you cannot use that. You can't. So don't make that mistake if I put that problem in the first exam. Right? If you're going to use the kinematic equations, you should know that these are only applicable when the acceleration remains constant as the object moves. Constant acceleration. Well, F equals ma, right? The only way for an acceleration to remain constant when the mass of the object stays constant is when the forces remain constant. But this force that this charged particle exerts on the other one is changing with distance. So therefore, as this particle moves from here to there, the force that this one exerts with which it pulls is getting bigger, 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 bigger. It's changing. It is not constant. Therefore, this analysis is completely wrong. No points are deserved over there. And it's sad to see someone lose 15 out of 15 points because, they use something like that. So, well, gee, how do you do it, right? If the force is changing, well, the work energy theorem. You also did another example where the force was changing in physics 185, when you had a mass attached to a spring, the force exerted by the spring was minus kx. And as x was changing, as the mass was oscillating about the equilibrium position, x was changing. So what did you do? No, you introduced the elastic potential energy, 1/2 kx squared, right? Mechanical energy is what you call it, 1/2 mv squared plus 1/2 kx squared. So you use energy arguments to solve that problem. What happens in the case of gravity, in physics 185, if we have an object that's interacting with the Earth, let's say this is the Earth, and the object whose motion you're considering is so far above the surface of the Earth that, if it goes from here to there, right, over these distances, if the Earth looks like that, the force of gravity is changing. So you do not use this. You do not use this at all. Instead, you use again energy arguments, except that in this case, the gravitational potential energy, if this is m1 and this is m2, is that. So then you use, the work energy theorem. So in many cases, one of the forces acting on the object may be changing with position. That makes the acceleration not a constant, and therefore you cannot use the kinematic equations. So what's going to save you is the work energy theorem. So, know the difference between, so this here is wrong. E is kq over r squared, right? V is kq over r. This is actually a vector, right? Now, force is q prime times E, and energy, electrical potential energy, is q prime times V. So I call this external. I call this external. So this would be the external electric field as far as q prime is concerned, and this would be that. So understand, think about, what's the difference between this and this? And the difference between this and this, and the difference between this and that, right? This was chapter 21 and chapter 22. We'd spent, all of chapter 22 on Gauss's law just calculating electric fields so that we could use this expression. Now, in chapter 23, we introduce this so that we can calculate electrical potential energy. Yes?
Why did you put a prime on the Q charge?
Because this charge is not the same as that. Because, right, this is the potential at the location of this. So this potential could not be kq prime over r. I mean, if I say this is q prime, and suppose I say this is k q prime over r, well, r is 0, because this charge is the same as this. Because this is the potential at the location of this, and then this is undefined. Right? Notice that I call this q and q prime. If I take that and I plug it in here, I get k q prime q over r. See, the energy of interaction between these charges depends on both of them. If I'm talking about energy, it's the energy of interaction of this with that. So it has to do with both of those charges, like over here, right? If I want the gravitational potential energy of the object as it interacts with the Earth, right? This is r, right? So m1 is the mass of the Earth, and m2 is the mass of the other object. It is an energy of interaction between the Earth, which is one mass, and the other object that's moving in the vicinity of the Earth. So the energy has to do with both of them. Right? Just like the force. If I take that and I plug it in here, this would be k q prime q r hat over r squared. So the force describes an interaction between the two charges. One charge exerts a force on the other one. So there you have the reference to both of them. the energy, reference to both of them. But if you're talking about electric field, you don't need to have another charge. One charge alone will generate an electric field around it. But one charge alone cannot exert a force on itself. And that's equivalent to this. So, know the difference between these two, and know the difference between these two, and the difference between these two. That's what, the formulas are very simple. You can memorize them, but do you know what they mean? If you don't know what they mean, you'll use them incorrectly in a problem, and then therefore get the problem wrong. So you have to know what each one of them means and what are their limitations. When I write k cubed r squared, I cannot ask you for the electric field at r equals 0 at the location of the charge that's producing that electric field, because I'm dividing by 0. It's undefined. I can only ask you for the electric field that the point charge generates at locations away from it. I can only ask you for the electric potential that a point charge generates away from it. Like over here. I can ask you what the electric potential is here, there, any place, but not over there. Because then it would be 27 divided by 0. It's undefined. But if I put another charge over here, like I did here, there, then I can calculate the electric potential over there, generated by that one. So why do I even care about the electric potential over here? Because I need that potential to then multiply by the charge that I put there to figure out the energy of this charge. Okay? So, this 13.5 volts came from this one. But the minus 27 volts came from this number and the charge. So, think about it. Don't just write it down and say, they're just formulas where you plug things in. It's easy to plug in numbers over here, right? We all know how to use a calculator. But think about, I appreciate your question. Why is this Q and why is this Q prime? There's a reason why I put a Q prime in there. Because this V is not the one generated by this. This is the potential at the location of that generated by some other charge. Well, by Q, not Q prime itself. So, should we call it a day, I think? I don't know. I think around now is when we're supposed to be finishing, right? Yes?
We've been talking about like the electric potential energy closer to Q is smaller than the one further, but what if the Q prime is a positive charge?
Good question, I love it. What if this charge is negative, for example? Well, we have that, right? So this potential would be what? Negative, right? Right? And this potential would be negative. And this potential would be negative. And suppose I put the same charge of minus 2 coulombs, right? Suppose I put the same charge. Let me just get rid of this one. So what would be the energy of it? It would be plus 54 joules, right? And that would be minus 2 times minus 13. That will make it plus 27. And there will be minus 9 times minus 2. That will be plus 18. So when I release this charge over here from rest, it's going to say, if I go that way, well, here my potential energy is 27 joules. If I go that way, it's going to be 18 joules. And if I go this way, it's going to be 54 joules. Which way do you think it's going to go?
Right.
To minimize its potential energy. And as it goes that way, what's going to happen to its speed? What's happening to the potential energy? It's getting smaller, which means it's getting converted to kinetic energy. So can you see? Now another way of looking at it is you can say, that's a negative charge, this is another negative charge, they hate each other, it pushes it away, and it goes away. Or you could say, this is a negative charge, it generates an electric field this way, right? At that location where I place the other charge, so if I want to know the force on this, right? Well, this charge is negative, right? So therefore these two vectors have opposite directions. Since the electric field there is towards the charge, because that one is negative, the force is going to be this way. So it's going to be repelled by it. Cool?
So the U depends on the charge of the second.
When dealing with electric potential and potential energy, these two quantities are scalar quantities. The only way to account for the fact that it's a negative or positive charge is to use those charges, those signs, you gotta put them in here. With electric fields and electric forces, they're vectors. So the way that I do it is I calculate the magnitude and then I remember if the charge is positive, it generates an electric field pointing away. If the charge is negative, it generates an electric field pointing towards it. And then this is a scalar times a vector that gives me a vector. This vector is going to have the same direction as that if this scalar is positive. And this vector is going to have the opposite direction as that if this scalar is negative. That's the fundamental. That's what you cannot afford to forget. Once you do a lot of this, you realize that there are only so many things that you should really, really know. Go back to the definitions and fundamentals. So we keep going back at it.
Can I ask a question?
Yes?
What is the unit vector? Is that a V with a hat?
This is a unit vector in spherical coordinates.
Oh, okay.
So if the charge is here, let's say plus Q, right? So if I'm at a distance R away, right? So instead of, the electric field is going to be this way, right? So, gee, I could write that as, Ex I hat plus Ey J hat plus Ek K hat, right? Ez. But that's too complicated. It is better to just use polar coordinates.
Okay.
Actually, spherical coordinates because it's in 3 dimensions. And so R hat is a unit vector in the direction that this variable increases. Negative R hat would be this way. So for example, if the charge is negative, I can take this minus charge, minus sign, and put it in here. And then if it's negative, then negative R hat means that the electric field is going to be towards the charge, if the charge is negative.
Okay, thank you.
Okay. I think we have lab today, right? We're gonna finish that experiment from 2 weeks ago on the oscilloscope, and we're just gonna try to make a couple of measurements. So 6:45, right?
Yeah.
Yeah.
All right. I'll see you later.
Whoa, you can go, right? Holy shit.
No, I put mine.
Oh. Okay, sure.
That just,
I saw the phone.
I can't stop recording.